Dimensions are essential to understanding the meaning of a variable. They are also abstractions and may not be interpretable on their own without additional context. Let's look at an example of potential confusion where two variables with very different interpretations have the same dimensions. Density is a property of matter that relates how its mass is distributed across the volume of space it occupies. Typically, we talk about density as the amount of mass per unit volume. Hopefully, the dimensionality of density is clear at this point, and that the mass of a given substance divided by the volume of that substance would simply yield dimensions of mass per volume or mass per length cubed. The abstract character of dimensions is illustrated by other different variables that also have dimensions of mass per volume. For example, the concentration of a solute in a solution is commonly reported as the mass of the solute normalized to the volume of the solution. So without specific context, it appears we have two variables with comparable algebraic derivations leading to the same dimensions of mass per volume, and perhaps creating the misconception that these two variables mean the same thing. Before attempting to interpret these dimensions, you should ask yourself contextual questions like which mass is being discussed and which volume is being discussed, before you conclude what dimensions like mass per volume might mean. The need for additional context is also emphasized in that the same concept might be represented by many different dimensions. Therefore, a variable referenced with the same name might actually be a different variable depending on the dimensions used. For example, the concentration of a solute in a solution might be characterized in many different ways. We might talk about the mass of the solute relative to the mass of the solution rather than the volume of the solution. In this case, the mass in both the numerator and denominator divide out to unity, meaning the concentration in this case is dimensionless. Volumetric ratios are a common way to report the alcohol content of beer or wine. The units are often in percent, but concentration is still fundamentally a dimensionless quantity, with the volume of the numerator dividing out with the volume in the denominator. Here we have two different conceptualizations of concentration that have the same dimensions, but definitely do not produce the same number except in very specific situations. A common way to avoid this ambiguity is to report the non-simplified dimensionless ratios. For example, you might specifically designate a mass ratio as a mass per mass, or you might specifically designate a volumetric ratio as a volume per volume to avoid any accidental confusion with the mass ratio. Chemists concerned with stoichiometric calculations will often report concentrations in molarity, which is defined as the count of solute molecules normalized to the volume of the solution. Molality is another common dimension of concentration where we consider the count of the solute per mass of the solution rather than the volume of solution used in molarity. This isn't even the end of the list of potential dimensions for concentration. But hopefully I've made the point that context is everything when it comes to appropriate interpretation of how a given dimensional analysis reflects the real world.